All right, let's resume this. Now, the third part, you got your acid-base balance. Here we will define a buffer. We'll define the different types of buffer, by the way, which is bicarbonate, phosphate, and protein buffers. We also will define how the kidney controls hydrogen ions and how we actually save or let it go, depending on the acid-base balance. We'll define the types of acidosis and alkalosis, and then also see if it's a respiratory urinary system that's helping to balance this. Metabolism has a lot of enzymes, which is sensitive to pH. Any deviation can either slow down metabolism or increase metabolism. Now, acids are chemicals that release H ions because they have a lot of H ions. And there's also a strong and weak acid. Now, the bases also have a strong and weak basis, where strong bases like hydroxide ion helps to take in and raise pH faster. A base is any chemical that accepts H ion because it doesn't have H ion. So a base is an electron or H ion acceptor, while an acid is a donor. Remember this number, put this in your bag of normals, 7.35 to 7.45 pH range of the blood. Any changes or insult or tendency to change this can lead to either going down below 7.35 acidity or going up above 7.45 alkalinity. Also, lactic acid can contribute to any acids because of metabolism can also affect this. This is 7.35 to 7.45 pH level of the blood, the blood itself. Because you can have the gastric secretions at pH level of 2 and even 1 because it's hydrochloric acid. So what we're talking about is of the blood. But keep in mind, wherever the blood goes, that organ is understood to have that type of pH balance in their tissues. Okay, so uh, other acid sources are lactic acid for anaerobic procedures, phosphoric acid, fatty acid and ketones from fat breakdown, carbonic acid for carbon dioxide. All right, so a buffer is any mechanism that resists change in pH. It tries to balance the acid and the base parts or the alkaline so we'll stay in the right level. Now, there's two physiologic buffers. It's a urinary system and the respiratory system. It's physiologic because it's a natural buffer of the body and actually involves major organs. Urinary system uses the kidney, ureter, urinary bladder, and urethra, while the respiratory system uses the lungs and its uh, ducts or into the trachea as well. Of course, you have your alveoli. Now, the difference between this is the respiratory system is more faster in response. You can right away do some balancing. Now, the urinary system may take a few minutes before it actually balances, or depending on how much blood is passing through the kidney. But the respiratory system is not as a big buffer changer as the urinary system. The urinary system, once it gets going, can convert or take out a lot of acid or a lot of base in the urine more than the respiratory system can, but it usually starts slower. Almost comparing endocrine with the nervous system. There are chemical buffers. We have physiologic buffers that we just mentioned. There's chemical buffers. For the chemical buffers, you have a substance that binds H ions and takes it out from the solution, and then the balance changes. Okay, the buffer system uh, is a mixture composed of acid or weak bases. There's three basic chemical buffers. You have the bicarbonate, the phosphate, and the protein buffer system. Let's go for the bicarbonate. This equation is very important. I need you to remember this. CO2 plus water plus H2CO3 or carbonic acid, bicarb HCO3, and H ions, which is hydrogen ions. Huh? This equation, remember this, number one, that H ions is acidity. If you have a lot of H ions, you're very acidic. If you have less, then you're less acidic, probably can be affected by alkalinity. Now, this equation may tend to go towards the right, where the product is more H ions here, or it can have the tendency to go to the left, our left, which the product is too much, is a lot of CO2. Now, this will happen depending on what's being balanced. All right, good. If we have too much H ions, for example, you have a diabetic situation where the patient is having a lot of H ions because of converting to, especially proteins, into possible glucose fats, basically fats into glucose, you will form ketone bodies. Ketone bodies will lead to increase in acidity. So you're on the right side of this equation. In order to compensate, the body will combine that H ions to buffer to your bicarb and will end up becoming carbonic acid here. Carbonic acid will further break down into your water and carbon dioxide. Carbon dioxide will be expressed out through the respiratory system. In fact, it will come up as deep breathing, heavy breathing. We call it Kussmaul breathing. Really deep breathing, almost like it makes a uh, growling sound. Now we're trying to convert H ions to become water and electro and carbon dioxide. Water you can dispose of in the body or use it. Carbon dioxide will end up becoming a gas being pushed out of the body. Right. So right there you see us being acidic first, and then the bicarbonate buffer system converting it to carbon dioxide so we can change the environment from too much acidity to something more controllable. Now, this equation at the same time can go to the other side, to the right, the opposite. How that happens is when you have a respiratory situation like asthma, and basically carbon dioxide is having a hard time going out. When that happens, you end up accumulating the amount of carbon dioxide in the lungs, right? Especially just before it comes in. And when that happens, it will convert to the increase of carbon dioxide due to asthma is because it cannot escape or cannot uh, be expressed in expiration. The vessels or the conducting tubes are tight because of the asthmatic reaction. You will now increase in carbon dioxide. If you have a lot of carbon dioxide in the tubes or the bronchus, which is eventually going to reflect on the alveolus, therefore you have more on the alveolar side than in the blood side. So carbon dioxide will tend to go back to the blood. Now, going back to the blood, it will combine with carbonic acid and then it will break into bicarb and H ions. So now you increase H ions ultimately. You increase acidity, and therefore it can lead to respiratory acidosis. It's an acidosis, but I said respiratory because the problem is in the breathing at this point. So that's respiratory acidosis, huh? So now you're in acidotic state, right? And with that said, the organ or system that can help you bring it out would be your chemical buffers and also your physiologic, which is your urinary. Okay, so it's a like all hands on deck system, and this bicarbonate shows you what happens. If it goes to, again in summary, if it goes towards the right, then you are increasing H ions, okay, and you'll end up in acidosis. If it's going to the left, you probably have a lot of H ions to begin with, and you're actually converting it to CO2 so you can avoid hyperacidity. Okay, now the bicarbonate buffer system coordinates with the lung and kidneys to help control pH and carbon dioxide. To lower the pH, the kidney will secrete bicarb, and to raise the pH, the kidney would excrete H ions, leading to alkalinity. Bicarb, because it's the byproduct of carbonic acid breakdown also, or buildup. Okay, now moving on, we have the phosphate buffer system. The phosphate buffer system is controlled by this equation. H2PO4 will result in HPO2 and H ions. So again, you see H ions. H ions is the acidity here. So if you are in an acidic environment, then you will have a lot of H ions. But you need to control or defer this into another situation. So the H ions will combine with your HPO4 or HPO2, and it will end up in H2PO4, right? This will take away the acidic H ion and combine it so it lessens the acidity of the environment. This is when you are in an acidic situation. Now, if you're in alkalinic, actually, yeah, that's a situation when you have too much ions, H ions. Now, if you need H ions because you're alkaline, then you use H2PO4, break it down, and the byproduct is H ions. Now, in acid-base balance, always remember where you are. Are you on the side that's just increasing in acidity or alkalinity, okay, which is a disease process, right? For example, in diabetes, we're using a lot of ketone byproducts. As a result, then it makes a lot of H ions. So that's a way of the disease. Compensation is when the body uses the bicarbonate or or even phosphate buffer system to catch all H ions and then bring them in an equation or situation where they are being used to favor alkalinity. Okay, so that's another method. And it actually helps the pH balance a lot. Now, the protein buffer system works in a different method. The protein itself has carboxyl and amino group. Now, the carboxyl, you see the COOH there. The H there is a part of the side group, and an H that this protein can donate in case you need H ions. When the pH begins to rise, rising means you're going above 7.4, and therefore you're becoming alkaline. Remember, it's 735 to 7.45. So, I mean, if you go above 4.5, then you're becoming alkaline. And so, protein will release the H ions in COOH, which is a side group of it, and donate the H ions. So, you become a little bit acidic. If you're alkaline, then you need a little acidity, right? That means you're above 7.45. You want to go below to get back into the 735, 7.45. So that's when you need H ions. You're a little bit alkaline to begin with. But if you're acidic, protein also can help. And what it will do is it will uh, use its amino side group to bind H ion when the pH gets low. So when your pH is low, that means you're below 7.35 and you have a lot of H ions. So the amino group of protein will bind the excess H ion that it sees and help you bring you back to 735, 7.45. It's very dangerous to be outside of this uh, scope, That's why we try to maintain it within 7.35 to 7.45. There you go. So that's the third chemical buffer, We started with bicarb, then we had your protein buffer and your phosphate buffer. Now, the goal is to make sure that you are between 735 to 7.45. Huh? The bicarbonate buffer system is the basis for the strong buffering capacity of the respiratory system. Right? It neutralizes 2 or 3 times as much acid as the chemical buffers. All right. Okay, good. It is when you remove or control the CO2, huh? All right. The same thing that we described a few minutes ago. The kidney can neutralize more acid or base than the respiratory system. Huh? And you try to remember that. Renal tubules secrete um, items into the tubular fluid. Huh? It could be bicarbonate, ammonia, or phosphate, and which are bound and free H ions are also controlled in that way. And because of this, you're able to help balance the bicarbonate levels. Huh? This basically shows the secretion and neutralization of H ions in the kidney. Huh? And if you need H ions, it will be saved in cases of alkalinity. And if you are in acidity, it actually will be disposed of by the kidney. Huh? All right. This actually uses the same bicarbonate buffer system. As you move it from one leg to the other, it will show you how you convert or save H ions. Uh, this tells us that the buffer system helps to maintain the H ions. Huh? So if the H ions are needed, we save them, and if they're not needed, we tend to dispose of them, huh? Or secrete them. Phosphate system are basic phosphate also in the glomerular filtrate. Ammonia is also a byproduct of this situation. This also shows basically the bicarbonate equation is what's happening here. As it goes through this pathway, right, where sodium is in exchange with potassium, then you have sodium back. You can create a pool that makes the acid be controlled, huh? So if we need to take away the acid, we uh, secrete it, but if we need to save it, we absorb it so we can balance the metabolism and the electrolyte inside our body. Taking a view of this, this is the balance. You are between 735 and 7.45, right? Feast your eyes on that for a few seconds. Notice that 7.35 to 7.25, okay, 7.35 to 7.25, okay, is almost just a few changes. But if we move just one unit, 7.35 down to 6.35 even, huh? Not even reaching one unit down lower, you will also already have damaged a lot of organs in your body and you are in acidity. 7.35, take one becomes actually 6.35. But before even reaching that, you would have destroyed your organs, huh? And probably even be dead by that time, right? So this is how a few movements down towards acidity can be drastic for the body and the buffering system. Okay, so on the other end of the field, 7.45. Let's say one unit is 8.45. You will not even reach that. By the time you get to about 8.0, a lot of organs have been damaged already, right? So it's very, very thin. And you would say, well, how come this is a thin margin, but the body doesn't go into major situations right away? Well, this is like comparing it to the lake, a big lake. A rise by a few inches, you think is easily achieved. Well, no, because in order to make that even increase or decrease in levels, you would have made a huge water volume increase or deficit because of the width of the circumference or even diameter of the lake. The bigger it is, and just one or a few inches increase or decrease is a big amount already. See, same thing here. Although the margins are narrow, it takes a lot to even completely acidify or alkalinize the blood. See, huh? But if it does, ever does, it becomes really fatal. On the bottom, you see H2CO3, and here your HCO3. Notice that there's a lot of HCO3 versus the H2CO3. Well, what does that mean? If there's a lot of one unit to compare to another unit, that tells us that H2CO3 increase, just one unit of it, will completely throw the whole thing into acidity, okay, towards the left. While a bicarb, if you add just one, it will probably not take effect because the other side's really heavy. So you will end up becoming more on the increasing the number of bicarb in order to change the balance. It takes a lot, huh? So another way of looking at it is that H2CO3 is more potent, more drastic in its effect, huh? When the balance is being considered. Acidosis are pH of the extracellular fluid below 7.35, huh? Below 7.35. And we try to balance it, buffer it, but sometimes it really is strong, huh? This causes membrane hyperpolarization because if you are going into acidosis, pH goes below and you become more negative inside. If you're more negative inside, then that means you will become more polarized. In fact, you reach a hyperpolarization. And like we know, this prevents sodium from coming in when needed. You end up being weak, huh? Right? Because of that. Now, the other part is this is in the case of acidosis, huh? This can lead to confusion, disorientation, coma, and possibly death. Increase in acidity here may also mean increase in CO2, huh? Alkalosis is above 7.45, more towards alkaline. Huh? That's why it's alkalosis. A person cannot live for a few minutes if the pH is below or above 7.7. Very dangerous levels. But if your pH is above 7.45, you expect the patient to have uh, overstimulation. Overstimulation because a pH of 7.45, okay, will lead to alkalinity, right? Huh? And if there's too much alkaline, that can lead to your uh, convulsions, paralysis, and tetany. Huh? All right. And this is again the pH of the blood, huh? pH of the blood, where if you reach 7.45 and above, you become more alkalotic. Okay, all right. The reason for this is you don't have the H ions, so the H ions makes you more negative. In that case, you're being on the alkaline side means you're closer to negative 55 rather than being away from it, as in acidosis. Uh, too much less H ions makes the inside of the cell reach negative 55 faster. Now here you see acidosis and alkalosis. Huh? If there's too much potassium, what really happens, let's say you have a case of acidosis, and we know if you have acidosis, you have a lot of H ions. Okay, that's cool. Now, if you have a lot of H ions, this is a negative, huh? If it populates cellular, it shows us that it can go inside because it's more of it outside. So it happens, especially without face mask. or in the sense that you will end up having a lot of H ions, huh? Meaning you actually keep a lot of H ions. If you have a lot of H ions from the outside of the cell, then it will tend to go inside. If it goes inside, you now have H ion and potassium inside. Now, remember, H ion is a positive. So if you have a positive inside the cell and a positive potassium, what happens is potassium becomes repelled to go outside. And also that this gives us that potassium is less outside. So by diffusion, where you have more potassium inside the cell, it will tend to go out. So what would happen is you would lose potassium, it goes out, but you gain H ions, which is also positive. The problem here is that unlike potassium, which is not um, buffered by the systems inside the cell, the H ion can be buffered by your chemical buffers. And when it does, it will be neutralized. Therefore, it will no longer exert its positivity. So the resting membrane potential of negative 70 without the positivity will become lower and lower and lower, and your cells will become weak or obtunded. And if it happens in the nerve cell of the brain, then you become weak and you're not able to process signals. That's why this can lead to comatose. Huh? It's almost like a condition of comatose. Doesn't function. Okay? But that's what happens when you have too much acidity or H ions. Right. Now, having said that, um, it's important to realize that H ions actually can be countered by the proteins, by the buffers. Of all the buffers, protein buffer is what we call as the first responder because it's actually near or inside the cell already. So the reaction from it with any acid or base imbalance is one of the quickest. Okay. In alkalosis, you have a lot of potassium outside, and they will tend to go inside. And when it goes inside, you have a lot of positivity. Therefore, from a negative 70, you will reach negative 55 faster, and you'll end up in depolarization, which is leading to action potential. Now, in this condition, if the acidosis is because of a respiratory problem, then we call it respiratory acidosis. If it's because of the alkalosis is because of respiratory in origin, then we call it respiratory alkalosis. For example, in alkalosis, when you are hyperventilating, especially with emotions, you actually throw a lot of carbon dioxide. And you'll be low in carbon dioxide, you'll be low in H ions or positivity, you will end up being in the negative. And you're in the negative, you'll end up being less, or you'll end up becoming alkalotic. Right? Carbon dioxide is being expelled out faster than it should be normally. In acidosis, the situation happens because you have a lot of H ions, like we said, in asthma, in the alveolar side, because it can get out and then it comes back to the body to produce what we have discussed. If the acidosis is increased, the organic products are increased, like lactic acid, ketone bodies because of alcoholism, diabetes, then it results in acidosis, and we call this your metabolic acidosis. In metabolic acidosis, you end up to become below 7.35. In metabolic alkalosis, the lung is working, so you can expect respiratory compensation to help with the acidosis that's happening right now. Diabetes and alcoholism can result in metabolic acidosis. They're similar in the sense that in diabetes, you actually are eating, but you're not able to make use of the food. While in alcoholism, you can actually eat, but you don't eat a lot because you spend your drinking. So you're like having an issue with nutrition right away. See? So, best thing we can do with that is to use the chemical buffers and use the respiratory system to compensate, right? And then you can resolve this metabolic acidosis. Now, if the natural mechanism, natural buffers of the body is not enough, it's not enough to bring us back to 7.35, 7.45, then we need to use other medical facilities or equipments to help us compensate and go back to the right level. We call this compensated acidosis, or we call this, if the body is able to do it by itself, then we call it compensated acidosis or alkalosis. If it needs other interventions, then we call it uncompensated acidosis and alkalosis. All right, huh? All right, like we said, in the respiratory, it will do in its capability to maintain. If you're going to become too acidic, it will try to expose or take out the. If you're in acidic, it'll try to convert back to CO2, so we can take out the effect of the acid, and that takes you out from acidity. If you're alkaline, we try to save the CO2 so they can convert as H ions and bring you a balance, right? Huh? The kidneys will either throw out H ions or save H ions, depending. Huh? In compensated metabolic acidosis, then we try to get rid of the H ions. If it's alkalosis, we try to keep the H ion and its resources. Huh? All right. So there you go. Huh? There you go with the acid-base balance. All these three balances are important. Huh? You have your water balance, electrolyte balance, and acid-base balance. Sometimes a patient is being wheeled inside the hospital. First thing they want to check if it's standing and just went into acidosis or alkalosis. Then we try to check if we can restore the right volume or the right situation, huh? And that's, it could be many imbalances for that unconscious patient. Could be an electrolyte imbalance, a water imbalance, or even a imbalance with your acid and base. All right, we'll take a quick break again before we move on to fluid replacement therapy, which is the next topic. Okay. All right.